Table charts are often used in environmental science and other fields when detailed, exact values need to be presented and analyzed. What is a table chart? A table chart is a data representation method that organizes information into rows and columns. Each row represents an individual data point or category, while each column contains specific attributes or variables of that data. It is useful when presenting multiple attributes or values for each category or when you need to show exact values without relying on visual approximations. Components of a table chart. Rows. Each row represents a distinct data point or category. In environmental science, this could represent individual pollutant sources, land use types, or species in an ecosystem. Columns. Columns represent the specific attributes, variables, or measurements associated with each row. For example, if you are presenting data on pollutant levels, columns might include different types of pollutants, measurement units, or time intervals. Header row. This is the first row of the table and contains labels for the columns. These labels describe the variables or measurements being represented in the table. Cells. The cells of the table hold the actual values. Each cell contains a specific value related to the category and variable defined by the intersecting row and column. Types of table charts. Simple table. A basic table that lists data values in a row column format without additional visual elements like color coding or highlighting. Complex table. A table that includes multiple attributes or variables for each data point. It may include subtables, additional columns, and may be used for presenting more advanced analysis, such as multidimensional environmental data. Frequency table. A type of table used to display the frequency or count of categories within a dataset. In environmental science, it could be used to show the number of occurrences of a particular pollutant or species in different environments. Comparison table. A table used to compare different categories, regions, or time periods. This type is useful in environmental science to compare pollutant levels across multiple sites or years. How to construct a table chart. Step 1. Identify the categories and variables you need to represent. For instance, if you are presenting data on air pollution, the categories could be different cities or regions, and the variables could include various pollutants, e.g., nitrogen dioxide, sulfur dioxide, carbon monoxide. Step 2. Label the rows with the categories you are studying, e.g., city names, species, etc. Step 3. Label the columns with the variables you will measure, e.g., pollutant levels, population size, temperature. Step 4. Fill in the data cells with the corresponding numerical values or information. Step 5. Check for consistency and accuracy. Ensure that the data is correct and that each row and column is appropriately labeled. Step 6. Optional. Enhance the readability of the table by using color coding, bold fonts, or highlighting specific values that need emphasis. Advantages of table charts. Accuracy and precision. Unlike visual graphs, table charts display exact numerical values, making them ideal for conveying precise data. Clarity. Tables can display a large amount of detailed data in a compact, easy-to-read format, which is helpful when exact comparisons or specific details are necessary. Comparison. Tables are particularly effective for comparing several variables or categories side by side, allowing easy identification of differences between them. Data organization. Tables help organize complex data in a structured manner, making it easier to navigate and analyze. Disadvantages of table charts. Lack of visual appeal. Table charts do not provide a visual summary of data trends or patterns, which makes it harder for the audience to quickly interpret the data. Not ideal for large datasets. For large datasets, tables can become cumbersome, making it difficult to absorb the information at a glance. In such cases, graphs or charts may be more suitable. No immediate insight. While tables offer detailed information, they do not immediately offer insights into the data's meaning or implications. A pie chart or bar graph might be better for showing trends or proportions. Examples of table charts in environmental science. Pollutant concentrations in different cities. A table can display the concentration levels of various pollutants, e.g., nitrogen dioxide, sulfur dioxide, ozone, across different cities or regions. Rows. City names, e.g., City A, City B, City C. Columns. Pollutants, e.g., nitrogen dioxide, sulfur dioxide, ozone. Cells. Numeric values representing pollutant concentrations for each city. Example. City nitrogen dioxide ppm, sulfur dioxide ppm, ozone ppm, city A 0.035, 0.020, 0.075. City B 0.045, 0.030, 0.080, city C 0.025, 0.015, 0.070. Land use distribution in a region. A table could be used to represent the distribution of land use types across different regions within a country. Rows. Regions, e.g., Region 1, Region 2, Region 3. Columns. Land use types, e.g., residential, commercial, agricultural, industrial. Cells. Values representing the area, e.g., in square kilometers of each land use type in each region. Example. Region residential, square km, commercial, square km, agricultural, square km, industrial, square km, region 1, 150, 30, 500, 50. Region 2, 200, 40, 600, 80, region 3, 180, 35, 550, 60. Species abundance in different habitats. In environmental science, a table chart can display the abundance of species in different habitats, showing how species are distributed across multiple environments. Rows. Species, e.g., species A, species B, species C. Columns. Habitats, e.g., forest, wetland, grassland. Cells. The abundance of each species in each habitat. Example. Species forest, abundance, wetland, abundance, grassland, abundance, species A 50, 3020. Species B 604030, species C 705040. Guidelines for using table charts. Label clearly. Ensure that each row and column is clearly labeled to avoid confusion. Labels should be precise and reflect the variables or categories they represent. Keep it simple. Avoid adding unnecessary rows or columns that do not contribute to the analysis. Keep the table as focused as possible. Organize data logically. Arrange the data in a way that makes it easy to interpret. For example, sort rows or columns in descending order or group related data together. Highlight key data. Use bold fonts or shading to highlight important data points or comparisons, especially when dealing with large datasets. Previous year questions. Which of the following is a major advantage of using a table chart? A. It is visually appealing. B. It provides exact values for comparison. C. It is ideal for showing trends over time. D. It makes data easier to interpret visually. Answer. B. It provides exact values for comparison. Year, 2021. Which type of table chart is best for showing the frequency of pollutants in different environmental zones? A. Simple table. B. Comparison table. C. Frequency table. D. Multi-dimensional table. Answer. C. Frequency table. Year, 2020. When would a table chart be more appropriate than a pie chart? A. When you need to represent proportions visually. B. When you need to compare detailed numerical values across multiple categories. C. When you need to show trends over time. D. When you have data for more than 6 categories. Answer. B. When you need to compare detailed numerical values across multiple categories. Year, 2019. What is a key limitation of table charts? A. They are difficult to construct. B. They lack visual appeal for large datasets. C. They cannot represent numerical data. D. They are not effective for categorical data. Answer. B. They lack visual appeal for large datasets. Year, 2020. What should be included in the header row of a table chart? A. The data values. B. The category names. C. The column labels that describe the variables or attributes. D. The summary of data. Answer. C. The column labels that describe the variables or attributes. Year, 2021. Table charts are one of the most structured ways to represent and compare data. They are essential in presenting exact values and ensuring clarity when multiple variables need to be displayed. By organizing data systematically, they allow for a detailed and precise analysis, making them an indispensable tool in environmental science. You said, line chart. ChatGPT said, line chart. A line chart is one of the most commonly used graphical representations in environmental science and other fields to display data trends over a continuous period. It is particularly useful when you need to observe how a variable changes over time or across a series of ordered categories. In a line chart, data points are plotted on a graph, and they are connected by straight lines, providing a clear visual of trends, fluctuations, or patterns. What is a line chart? A line chart is a type of chart that displays data points, usually representing values at specific intervals connected by straight lines. It is typically used to represent quantitative data, where the relationship between the data points is continuous and can be connected logically over time or categories. Components of a line chart. X-axis, horizontal axis. This axis typically represents the independent variable, such as time, e.g., years, months, days, temperature, or distance. It is the axis that lays out the intervals or categories over which the data changes. Y-axis, vertical axis. The y-axis represents the dependent variable, i.e., the values that change according to the x-axis. In environmental science, this could represent measurements like pollutant concentration, temperature, or population size. Data points. These are the plotted values on the graph that correspond to specific points on the x and y axes. Each point represents an observation or measurement taken at a given time or category. Line. The line connects the data points in a smooth fashion, which helps in understanding trends or fluctuations in the data over time or categories. Grid lines. These are horizontal and vertical lines that help to reference the exact values of the data points for better accuracy. Legend optional. If the chart represents multiple data sets, e.g., comparing different pollutants over time, a legend can be included to differentiate the data series. Types of line charts. Single line chart. A chart with one line connecting data points. This is used to show the trend of a single variable over time or categories. Multiple line chart. A chart that includes more than one line, each representing a different data series. It is used to compare trends of different variables over time, such as comparing the pollution levels of multiple cities or different pollutants. Stacked line chart. This is used when the total of multiple data series is important. The areas under the lines are stacked on top of each other to show the cumulative value. In environmental science, this could be used to show the total environmental impact of multiple pollutants over time. Smooth line chart. A variation of the line chart where the lines are smooth to reduce noise and emphasize the overall trend. It is useful when the data fluctuates frequently and you want to highlight a general trend. Advantages of line charts. Trend visualization. Line charts excel at displaying trends over time or across ordered categories. They make it easy to identify upward or downward movements, peaks, and troughs in the data. Clarity. Line charts provide a clear and simple visual representation, making it easy to compare the changes in values between different time periods or categories. Multiple data sets. With multiple lines, you can compare several variables or categories at once. For instance, you can compare temperature changes across different cities or regions using one line chart. Continuous data representation. Line charts are perfect for showing continuous data and for any variable where values are connected logically over time or sequential categories. Predictive insights. By examining the slope of the lines, you can infer trends and even predict future data points, making line charts a good tool for forecasting and analysis. Disadvantages of line charts. Overcrowding. If too many lines are plotted on a single chart, it can become cluttered and difficult to read. The chart may lose clarity, especially if the data points of different lines overlap. Loss of detail. Line charts may oversimplify data, particularly if the underlying changes are small or irregular. Minor fluctuations can be hidden in the smoothness of the line, especially in smooth line charts. Inaccurate representation. If the data is categorical or the relationship between the variables is not continuous, a line chart may not be appropriate, as it could mislead the viewer into thinking there is a smooth or linear relationship. How to construct a line chart. Step 1. Determine the variables to be plotted. Identify the independent variable, e.g., time, and the dependent variable, e.g., temperature or pollutant concentration. Step 2. Prepare the data points. For a time series, organize the data points chronologically. If comparing different categories, ensure that the categories are logically ordered. Step 3. Set up the axes. Label the x-axis with the independent variable, time, categories, etc., and the y-axis with the dependent variable. Step 4. Plot the data points on the chart based on the corresponding values of the independent and dependent variables. Step 5. Connect the points with a line. If you are plotting multiple data sets, make sure each line has a distinct color or pattern for differentiation. Step 6. Add a title and axis labels. The title should describe what the chart is showing, e.g., pollution trends over time. Axis labels should specify what each axis represents, e.g., year, for the x-axis and pollutant concentration ppm for the y-axis. Step 7. Optional. Add a legend if you have multiple lines, to identify the different data series. Examples of line charts in environmental science. Air pollution levels over time. A line chart can show how the concentration of various pollutants, e.g., carbon monoxide, nitrogen dioxide, sulfur dioxide changes over time in a specific city or region. X-axis. Time, e.g., years or months. Y-axis. Concentration of pollutants, e.g., parts per million. Lines. Separate lines for each pollutant. Example. Year CO ppm, NO2 ppm, SO2 ppm, 2010 0.035 0.025 0.020 0.011 0.045 0.028 0.022 0.012 0.038 0.030 0.019 Line chart representation. A line chart plotting Colorado. Line chart representation. A line chart plotting Colorado. Number 2, and so 2 levels over the years. Temperature fluctuations in different seasons. A line chart can compare temperature variations across seasons in a particular region, showing the relationship between seasonal changes in temperature. Example. Month temperature degree C, January 5th. February 8th, March 12th. Line chart representation. A line chart with temperature variations plotted for each month. Guidelines for using line charts. Avoid overcrowding. If you are comparing multiple datasets, limit the number of lines on a single chart. If necessary, break up the data into separate charts to keep them readable. Ensure proper scaling. Ensure that both axes are appropriately scaled so that the trends and patterns are accurately represented. For example, if the y-axis is not properly scaled, trends could be exaggerated or minimized. Use distinct colors. For multiple lines, use distinct colors or patterns so that each line is easily identifiable, especially in complex charts. Label clearly. Include clear axis labels, titles, and legends if necessary to make the chart self-explanatory. Previous year questions. What is the primary use of a line chart in environmental science? A. To show the distribution of pollutants across regions. B. To show trends in pollutant levels or environmental parameters over time. C. To compare different categories of environmental data. D. To display exact numerical data without any trends. Answer. B. To show trends in pollutant levels or environmental parameters over time. Year, 2021. In the context of environmental data, which of the following is best represented by line chart? A. Annual rainfall data in a region. B. Species diversity across different ecosystems. C. The distribution of pollutants across geographical locations. D. Land use distribution in different regions. Answer. A. Annual rainfall data in a region. Year, 2020. Which of the following is an advantage of using a line chart? A. It allows for an immediate visual comparison of multiple categories. B. It is ideal for comparing categories with discrete data. C. It helps to display trends and changes over time. D. It is the best tool for presenting detailed numerical values. Answer. C. It helps to display trends and changes over time. Year, 2020. Which of the following data types should not be plotted on a line chart? A. Time series data on temperature. B. Concentration of pollutants over months. C. Different species present in various ecosystems. D. Comparison of air quality across multiple cities. Answer. C. Different species present in various ecosystems. Year, 2021. When comparing multiple environmental variables using a line chart, which should be kept in mind? A. The lines should be in the same color to avoid confusion. B. The x-axis must represent continuous data only. C. All variables should be plotted on the same scale. D. A pie chart would be more suitable for comparison. Answer. C. All variables should be plotted on the same scale. Year, 2020. Line charts are invaluable in environmental science, offering clear insights into how various environmental variables change over time or across categories. They enable trends to be observed and provide a simple but effective method for comparing multiple datasets simultaneously. You said, mapping of data. ChatGPT said, mapping of data. Mapping of data is the process of representing information visually on a map or chart, typically using geographical coordinates, spatial data, or other types of georeference data to highlight relationships, patterns, or trends. In environmental science, data mapping is essential for understanding the distribution of environmental variables such as temperature, rainfall, pollution, biodiversity, and land use, among others. Data mapping enables researchers and policymakers to better analyze geographical trends, identify spatial patterns, and make informed decisions regarding resource allocation, conservation efforts, and environmental management. It is especially useful in understanding how environmental factors vary across different locations and over time. What is data mapping? Data mapping involves the visual representation of data on a map, where variables are assigned specific geographical locations or regions. It can involve a variety of techniques, including the use of geographic information systems (GIS), which allow for the mapping and analysis of spatial and non-spatial data. Components of data mapping. Geospatial data. This is the location-based data that corresponds to specific geographical coordinates, latitude and longitude, or predefined regions, countries, cities, etc. Variables. The data that will be represented on the map, such as temperature, air quality index, rainfall, vegetation density, or species distribution. Mapping tool or platform. A software or platform that helps in visualizing and analyzing the data, such as Geographic Information System (GIS) or online mapping platforms like Google Maps. Legend. A key that explains what the different colors, symbols, or shapes on the map represent. The legend helps users understand how to interpret the map data. Scale. Scale. The scale of the map provides context on the size of the area being represented and the level of detail that is being shown. Types of data mapping. Choropleth mapping. A choropleth map is one where areas are shaded or patterned in proportion to the value of a variable being represented. This type of map is particularly useful in environmental science to show the concentration of pollutants, temperature variations, or land use changes across different regions. Example, a map that uses different shades to represent varying air pollution levels across different cities. Point mapping. Point mapping represents individual data points as symbols or dots placed on a map. This method is useful when you have discrete locations to map, such as sites of pollution measurements or wildlife sightings. Example, a map showing the locations of specific endangered species sightings in a conservation area. Heat maps. Heat maps use color gradients to represent the intensity of a variable across a geographic area. Higher values are typically shown in warmer colors, reds or oranges, while lower values are shown in cooler colors, blues or greens. This type of mapping is useful for identifying areas with higher low concentrations of a particular environmental factor. Example, a heat map showing the areas with the highest levels of urban air pollution. Flow maps. Flow maps are used to show the movement of variables over a geographic area. These maps use arrows or lines to represent the direction and volume of movement, which can help in understanding processes like wind patterns, water flow, or migration. Example, a map showing the flow of water in a river system or the movement of species across regions. Symbol mapping. This technique uses different symbols or icons to represent specific types of data at a location. The size or color of the symbol may indicate the magnitude or category of the data being represented. Example, a map showing the locations of deforestation activities with different sizes of icons representing the extent of deforestation. 3D surface mapping. This type of map is used to display data in 3 dimensions, allowing users to view how variables change not only horizontally across space but also vertically in height or depth. It is particularly useful for visualizing topography, elevation, or environmental factors that vary with altitude, such as temperature or precipitation. Example, a 3D map showing the distribution of forest cover and elevation across a mountainous region. Applications of data mapping in environmental science. Applications of data mapping in environmental science. Pollution monitoring. Mapping pollution data is a powerful tool to track the distribution and concentration of pollutants like particulate matter PM2.5, nitrogen dioxide, number 2, sulfur dioxide, SO2, and carbon monoxide CO. By mapping pollution levels, environmental agencies can identify hotspots and implement measures to reduce emissions in high-risk areas. Climate change studies. Data mapping is used to represent changes in climate variables such as temperature, precipitation, and sea levels over time and space. By mapping climate trends, researchers can analyze regional patterns and predict future impacts. Biodiversity and habitat mapping. Mapping the distribution of species and ecosystems helps in understanding biodiversity patterns. It aids in identifying critical habitats, migration corridors, and regions vulnerable to habitat loss or degradation. Natural resource management. Data mapping is essential for monitoring the availability and distribution of natural resources such as water, forests, and minerals. Maps can help in planning sustainable resource extraction and management, as well as monitoring the effects of overexploitation. Disaster management. In cases of natural disasters such as floods, wildfires, or earthquakes, mapping can help identify the areas most at risk, track the progression of the disaster, and plan for relief efforts. Land use and land cover mapping. Mapping land use changes over time helps in understanding urbanization, deforestation, agricultural expansion, and other human activities that impact the environment. It also helps in land planning and conservation efforts. Steps in data mapping. Data collection. The first step is to gather the relevant data. This could include satellite data, field measurements, sensor readings, or historical environmental data. Data preprocessing. Raw data needs to be cleaned and transformed into a usable format. This step involves ensuring that the data is accurate, removing outliers, and correcting any inconsistencies. Data integration. Data from different sources might need to be combined. For example, air quality data from sensors can be integrated with geographical data from satellite imagery to map pollution patterns. Visualization. After preparing the data, it is mapped onto a graphical platform using GIS software or other mapping tools. The data is represented using appropriate symbols, colors, and scales to enhance the visual clarity of the map. Analysis. The mapped data is then analyzed to derive meaningful insights. This could involve identifying spatial trends, making comparisons, and drawing conclusions that can be used for decision-making. Interpretation. The final step involves interpreting the map and its findings. Environmental scientists or policymakers will use the mapped data to develop strategies, solutions, or recommendations based on the insights derived from the visualization. Advantages of data mapping. Clear representation. Data mapping provides a visual representation that is often easier to understand compared to raw data tables or textual descriptions. Pattern identification. It allows for the identification of spatial patterns or trends that may not be obvious in numerical data. Decision-making support. Mapped data helps in making informed decisions regarding resource management, conservation, and environmental policy formulation. Public awareness. By mapping data, it becomes easier to communicate complex environmental issues to the public and policymakers, aiding in environmental awareness and action. Disadvantages of data mapping. Data limitations. Mapped data is only as good as the underlying data. Poor quality or incomplete data can lead to misleading maps and incorrect conclusions. Oversimplification. Maps can sometimes oversimplify complex data or mask finer details. For example, choropleth maps may not show interregional variations if data is aggregated over large areas. Technical challenges. Mapping data requires specialized tools, such as GIS software, and expertise in spatial analysis, which can be a barrier for some users. Example of data mapping in environmental science. Mapping air pollution levels. Air quality data for various cities are collected over a period. A choropleth map can be created where each city is shaded according to the concentration of pollutants. The map may show higher pollution levels in industrial areas compared to rural zones, helping policymakers target areas with the highest air quality concerns. X-axis. Geographic coordinates, latitude and longitude. Y-axis. Pollutant concentration ppm. Mapping type. Choropleth mapping, where different color gradients represent pollutant concentration. Previous year questions. Which type of map would be best used to represent the spatial distribution of temperature across different regions over time? A. Point map. B. Choropleth map. C. Heat map. D. Flow map. Answer. C. Heat map. Year, 2020. Which of the following would be an appropriate mapping technique to analyze species distribution in different regions of a forest? A. Line chart. B. Point map. C. Flow map. D. 3D surface map. Answer. B. Point map. Year, 2021. In which scenario would a choropleth map be most useful in environmental science? A. Showing trends in global temperatures over the last century. B. Displaying pollution levels in different cities across a country. C. Plotting the flow of migratory species across continents. D. Representing the population of species in different ecosystems. Answer. B. Displaying pollution levels in different cities across a country. Year, 2019. What is the key advantage of using a heat map in environmental studies? A. It shows precise numerical data points. B. It highlights the intensity of variables over a geographical area. C. It provides a comparison between different categories of data. D. It represents categorical data across regions. Answer. B. It highlights the intensity of variables over a geographical area. Year, 2021. Data mapping is a crucial tool in environmental science for understanding geographical patterns and relationships, and it plays a vital role in analyzing and managing environmental resources effectively. You said. Data interpretation. ChatGPT said. Data interpretation in environmental science. Data interpretation is the process of analyzing and making sense of data by applying statistical and analytical methods to extract meaningful patterns, trends, and conclusions. In environmental science, data interpretation involves understanding the relationships between environmental variables, predicting future conditions, and making informed decisions to address environmental issues. Effective data interpretation enables researchers, policymakers, and environmental managers to make data-driven decisions, plan interventions, and assess the impacts of different environmental factors. The ability to interpret data accurately is essential for conducting environmental assessments, monitoring pollution, studying climate change, and managing natural resources. Key steps in data interpretation. Data collection. Before interpreting data, it is essential to gather accurate and reliable data. In environmental science, data can be collected from various sources, such as satellite imagery, field observations, environmental sensors, historical records, and surveys. Data cleaning. Raw data is often messy, incomplete, or contains errors. Data cleaning involves correcting mistakes, filling in missing values, and ensuring that the data is ready for analysis. This step is crucial to ensure that the interpretation is based on accurate and reliable information. Exploratory data analysis. EDA involves examining the data visually and statistically to understand its structure, identify outliers, and check for patterns. Common techniques used in EDA include plotting histograms, scatter plots, box plots, and summary statistics like mean, median, and standard deviation. Statistical analysis. Once the data is cleaned and explored, statistical methods are applied to make sense of it. These methods include hypothesis testing, correlation analysis, regression analysis, and analysis of variance ANOVA. In environmental science, statistical techniques help in understanding the relationships between variables, such as the effect of temperature on species distribution or the correlation between pollution levels and health outcomes. Modeling and simulation. In many environmental studies, models and simulations are used to predict future trends or understand complex systems. For example, climate models can simulate future temperature changes based on current data, while pollutant dispersion models can predict the movement of pollutants in water or air. Data visualization. Data visualization is an essential part of data interpretation. Graphs, charts, maps, and other visual representations help in presenting the data in a way that is easy to understand and interpret. In environmental science, visualization tools like GIS, Geographical Information System, and heat maps are commonly used to interpret spatial and temporal data. Drawing conclusions. Based on the analysis and visualization, conclusions are drawn regarding the trends, patterns, or relationships present in the data. These conclusions help in making informed decisions and recommendations for policy or environmental management. Reporting and communication. The final step in data interpretation is communicating the findings. In environmental science, data interpretation results are often communicated through reports, scientific papers, policy briefs, or presentations. Clear and accurate communication is essential for ensuring that stakeholders, such as policymakers, environmental agencies, and the public, can understand the findings and act upon them. Methods of data interpretation. Descriptive statistics. Descriptive statistics summarize and describe the main features of a dataset. This includes measures of central tendency, mean, median, mode, measures of variability, range, variance, standard deviation, and measures of distribution, skewness, kurtosis. Example: in analyzing pollution data, the mean concentration of pollutants across different cities can be calculated to understand the average pollution levels in each area. Inferential statistics. Inferential statistics involve drawing conclusions about a population based on a sample of data. Techniques like hypothesis testing, confidence intervals, and regression analysis are used to make inferences about larger populations. Example: a hypothesis test might be used to determine whether a change in industrial emissions has led to a statistically significant increase in air pollution levels. Correlation and regression analysis. Correlation analysis measures the strength and direction of the relationship between two variables, while regression analysis models the relationship between a dependent variable and one or more independent variables. Example: a regression model could be used to predict the future concentration of pollutants based on factors like population density, industrial activity, and transportation patterns. ANOVA analysis of variance. ANOVA is used to compare the means of different groups to see if there are significant differences between them. In environmental science, ANOVA can be used to test if pollution levels vary significantly across different regions or over time. Example: ANOVA could be used to determine if air quality varies significantly between different seasons, summer, winter, monsoon, in a specific region. Time series analysis. Time series analysis involves analyzing data collected over time to identify trends, cycles, or seasonal patterns. In environmental science, this is often used to study climate trends, pollution levels, or species population changes. Example: time series analysis could be used to track the rise in average global temperatures over the last century and identify any significant warming trends. Geospatial analysis. In environmental science, geospatial analysis uses geographical data to interpret patterns related to the location of environmental variables. Geographic information systems (GIS) are commonly used to analyze spatial data, such as pollution levels, land use changes, and biodiversity distribution. Example: GIS can be used to analyze the spread of deforestation across different regions and its impact on local biodiversity. Common challenges in data interpretation. Incomplete or missing data. Environmental data may often have missing values due to sensor malfunctions, gaps in data collection, or inconsistencies. Handling missing data is a challenge that requires careful statistical techniques to avoid biased results. Solution. Methods such as imputation or using data from similar regions can help handle missing data. Multicollinearity. In regression analysis, multicollinearity occurs when two or more independent variables are highly correlated. This can make it difficult to interpret the results and draw meaningful conclusions. Solution. Using techniques like principal component analysis (PCA) or removing highly correlated variables can mitigate multicollinearity. Confounding variables. Confounders are variables that are not included in the analysis but can influence the relationship between the dependent and independent variables. Failing to account for confounders can lead to misleading conclusions. Solution. Including relevant confounding variables in the analysis or using statistical methods like stratification or multivariate regression can help address confounding. Overfitting or underfitting. In predictive modeling, overfitting occurs when a model is too complex and captures noise in the data, while underfitting occurs when the model is too simple to capture the underlying patterns. Solution. Balancing model complexity and validation techniques like cross-validation can help in preventing overfitting or underfitting. Applications of data interpretation in environmental science. Air quality monitoring. Data interpretation is crucial for analyzing air quality data from monitoring stations. By interpreting the data, environmental scientists can assess pollution trends, identify sources of pollutants, and make recommendations for improving air quality. Example: interpreting data on PM2.5 levels can help identify areas with high pollution and design policies to mitigate health risks. Climate change studies.